working on chapter 16. So we are talking about the thermodynamics. So what is thermodynamics? Let me see where it go there. Highlighter pen. So thermodynamics. So thermo means heat, H-E-A-T, heat. Dynamics means flow. So heat flows from one side to another side, and it is called thermodynamics. Ever see that? So for example, this is your beaker, and you have water here, and you put this guy in oven. So this is cold water, and this is a heater. So heat goes from heater to cold water or cold water to heater. Ever see that? How? What does happen? What does? Which phenomena it occurs there? Heat go from heater to water or water to heater? Who want to try? Heat goes from water to heater or heater to water? Heater to water. Because heater is too hot. Yes? So heat always flow from hot to cold. So this is too hot, very hot, and this is cold. So the high temperature, very hot means high temperature side to heat goes to the low temperature side. So this is called the thermodynamics. Make sense? Heat always goes from hot body to toward the cold body, and that is called thermodynamics. Thermo means heat, dynamics means cold. Ever got that? Thermodynamics. Yes, very important. Yeah, so we'll be using this concept all this chapter. Thermodynamics all the time. Now look here, spontaneous process. Spontaneous process. What is spontaneous process? Spontaneous means it happens itself. So if I put uh, I put this guy here like this, like this. You look here. So what happened? Did did it fall down or I push it down? It fall itself, right? So this is called spontaneous process. So look here, I try to put here like this, it just fall itself. I didn't do anything. So that's a spontaneous process. Make sense? If anything happens itself, that is a spontaneous process. Did I push you to come inside from outside? No, you come yourself. So it happened itself. That is called the spontaneous process. Make sense? So look here, somebody is coming, herself is coming. So that's called the spontaneous. You got that? So let's put, this is a mountain. This is the top of the mountain, and you try to put a ball here. Does that ball stay there or goes down? What happened? Yeah, it goes down. Itself or you need to push it? It itself goes down. So that's a spontaneous process. Falling of the ball from the slanting space down is itself a spontaneous process. Everybody see that? So water goes from, so there is a water here. Does water flow from up to down or down to up? Water goes from up to down or down to up? Down to up? Really? Water flows up to down. Yes? Water goes from up to down itself, right? So that's a spontaneous process. But if you need to put the water up there, you need to put a motor and then push water up there. Yes? Electric motor. Ever see that? So water goes from top of the hill to the down. So that's a spontaneous process. But water cannot go from down to up. So that's non-spontaneous process. Ever got that? Yes? Good. Right. Now look here. So if you mix, so if you have, actually you did this experiment in the general chemistry lab. So put some hydrogen here and there is some oxygen there. And then if you give a tiny spark of the matchstick, it all burns with a pop sound. Did you do that experiment? In the Gen Chem lab or foundation lab, we do that. Yes? So put a hydrogen and oxygen in a test tube and give a tiny bit spark of the matchstick and it just explode as a pop sound. So that's a spontaneous reaction. Everybody see that? So you look here. So you put a hydrogen in test tube and oxygen in test tube and give tiny spark. Spark means you just matchstick. You see that? You just scratch the matchstick and give a flame a little bit. Then hydrogen and oxygen just react and give the heat. Yes? So that's also the spontaneous process. So hydrogen and oxygen You mix in a test tube and give the spark, and water is formed itself. So you don't have to produce water. Yes, just mix hydrogen and oxygen and so the tiny spark, and you get the water. Yes, and then pop sound and heat. So that's a spontaneous process. Look here, in this one, in this test tube, you are putting some hydrogen, tiny hydrogen, and some oxygen here. So some hydrogen and some oxygen, two things. Give the spark, and then hydrogen bond with oxygen giving water itself. That's a spontaneous process. Yes, so from the previous slide, ever see that? Can you pass if I am not here? No, you cannot pass. No student can pass if teacher is not there. Yes? So this is not a spontaneous process. Passing a class is not a spontaneous process. You cannot do that. Yes? Ever got that? Yes, just like that. So passing a class is non-spontaneous process. It cannot happen itself. Yes? But failing a class is a spontaneous process. So if you don't want to come to the class, you don't take exam, whatever you want to do, that's a spontaneous, it happens. So, but to pass, you need to put effort. You need to come here, you need to sit in the class, and then you need to do a lot of work, and only you pass. So that's a non-spontaneous process. But if you want to fail a class, that's a spontaneous process. You don't have to come to class. You can come and go to the restaurant, whatever, and that's a spontaneous process. So if one process is spontaneous, the reverse is non-spontaneous. So passing a class is non-spontaneous. So failing a class is spontaneous. Ever see that? Yes or no? Just like that. Good. All right. Now look here. So this is a passing a class. S2O2 giving water is a passing a class. Now you want to break the water into S2O2. So this is a non-spontaneous process. Look here. So this is like a passing a class. You are producing water by putting some matchstick and mixing S2 and O2. So that bond and give a water is non-spontaneous. That's a spontaneous process. But if you take a water in a test tube, can you split water into hydrogen and oxygen? You cannot. You need to put a lot of electricity to electrolysis, and only you can produce S2 and O2. So that's a non-spontaneous process. You need to spend a lot of time there, effort there. You got that? So cooling water is spontaneous or non-spontaneous? Who want to try? So there is a hot water. So I want to put a hot water here. So let's do that one. So we don't have much, so we can do a little bit slow here. So let's look here. I have a hot water here. So I make a water coffee. So you go to the downstairs and you bought the coffee, hot coffee, HOT, hot coffee. Hot coffee. Now you bring it here. Does it become cold itself, or you need to make cold itself? Exactly. That's a spontaneous process. You got it? Spontaneous process. Now let's talk about the non-spontaneous process. Let's look here. Here is a water. So this is a cold water. You go home and get some water from the fridge and put it there. But you have a bad day. You have a cold. Now you want to drink warm water. Does this water become warm itself? 50 degrees centigrade. You want to drink the 50 degrees centigrade water. Does this water become warm itself, or you need to warm? Exactly, you need to warm. So warming water is not a spontaneous process. You need to put an effort, and it's a non-spontaneous process. Make sense? How about the cooking rice? Does rice cooks itself, or you need to cook it? You need to cook it. So that's a non-spontaneous process. Ever see that? How about you cook the rice and put in the room, and after 5 days it just decays and spoils? Is it spontaneous or non-spontaneous? Spontaneous. It just decays itself. Yes, you bought some banana from the Walmart and put in your home. After 10 days, what happens to the banana? All are ripened and decayed, right? So that's spontaneous. It's happened itself. Ever got that? Yes. All right, like this. Good. Let's go. So it happened itself is a spontaneous. If it doesn't happen itself, is a non-spontaneous. So what it is saying is that, so if you bond hydrogen and oxygen, do you feel hot, or you feel cold? You feel do you in your home, if you bond something, do you feel warm or cold? Bond something. So take a paper and light with a matchstick. Do you feel hot or cold? Hot, exactly. You see that? So hydrogen is like the paper. So look here, paper, and there is oxygen in air, and then you bond it, and it gives water and hot, heat. You see that? So it gives heat out. Therefore, you feel the hot. You see that? So this kind of reaction is called exothermic. So exothermic reaction. If you feel hot by doing something, that is an exothermic reaction. You got that? So if it is an exothermic reaction, they tend to be spontaneous. Ever see that? Just like the when you burn something, it gives heat, meaning that that happens itself. But not always. Most of the time, exothermic reaction happen themselves, but sometimes they don't happen. So look here, most of the time spontaneous reaction are exothermic, meaning that they give heat out, but not always. Sometimes they don't. They are not exothermic reaction. Ever see that? Sometimes exothermic reactions are not even the spontaneous. Yeah, but most of the time exothermic reaction happen themselves. Good. So if it is here, I just put it like this. I didn't do anything. It fall down. You see that? Did I fall it? It itself fall. Itself fall. So that's kind of exothermic. It happened itself. But sometime I need to push down. You see that? So for example, it's here. Does it fall itself down? No. So I need to just do like that and fall down. So that's maybe that's exothermic. It's falling down, but I had to push a little bit down. So most of the time, exothermic reaction happen itself. It's here, just fall itself. You see that? I didn't push. I didn't do anything. It was here, and I didn't fall it. It fall itself. But it's here, and I'm just throwing it down like that. You see that? So I did it. Yes. So both are exothermic. But to happen this one, I need to push it. But this happen itself. So most of the time, exothermic reaction happen themselves. But sometimes we need to do them. Everybody got that? Falling down is kind of exothermic. Everybody see that? So pulling up is endothermic, falling down is exothermic. It gives heat out or it gives energy out. Does that make sense? Yes? All right. Good. Now let's look here. Now this is a gas. You see that in this side there is a gas. This is empty, and there is a tap here. That the knob here. I open that one. If I open that one, does gas goes this way or no? Yes, yes or no? Yes. So if even not the gas, if this is a water and there is a tap here, if you open the tap, what happens? This water goes this side. Yes. Does it happen itself or you need to do it? You are just opening the tap. You are not just pushing the water. It happens itself. Everybody see that? So that's a spontaneous process. Does that make sense? So in home, you go to the home in your tap water and just turn the water knob a little bit. Does water come out itself or you need to pull the water? Itself. That's an exothermic process. Sorry, the spontaneous process. Yes? Everybody see that? Good, like that. Now I'm going to ask you, uh, is this system is more dispersed, or this is more dispersed? Which system is more dispersed? Dispersed means scattered. Which is a more scattered condition? This guy or this guy? A or B? B, exactly. So the system always tend to be dispersed. So this morning I go to the bathroom and then I just wash my hair and I took the comb and nicely comb my hair and I started to biking and my hair started to disperse. You see that? So if I need to make the hair, that's a less dispersed. You see that? Less dispersed condition. But when I go to home in the evening, I am just like a homeless person. All my hair is just like that. It disperses itself. Ever see that? So always the system try to disperse more. But if you don't want to be dispersed, you need to put effort not to disperse. You see that? So if I am not here, you guys are standing here and jumping and doing that and that, that's more dispersed. You always want to disperse yourself. You see that? But I am here, so you can't do that. Your teacher might notice me, he might fail me, he might introduce my name to the higher management, they might do something bad to me. So you are now a little bit afraid. You see that? So this class is in the not a disorder state. This is an order state. You see that? But if I'm not here, what happened? Oh, everybody's dancing. Maybe she come here, D goes there, and then you start to talk right like that. You see that? So this is a more dispersed condition. This is the less dispersed condition. Everybody see that? Yes or no? So more dispersed. So system always try to be dispersed more. If we don't want the system to be dispersed, what should we do? We should put effort and put everything together. If I want to do like that, I need to put effort. If I want to make like that, I just open the tap and everything is done itself. You got it? So I want to make this system like this system. So that itself happens and I need to do work. So I need to take all these guys this side and want to like that. And I want to make empty like this. I need to work there. So that's a less dispersed and it doesn't happen itself. I need to work there. Make sense? Good. Now look here. So this is a hot guy. This is a hot guy. So red means hot. So maybe this is a 100 degrees centigrade. This is a cold guy, maybe 10 degrees centigrade. You see that? So if I connect these two guys together with a wire, from which side heat goes to which side? From cold to hot or hot to cold? Hot to cold. Exactly. That happened itself. You see that? Ever got that or no? Yeah, so this is a 100 degrees centigrade, this is a 10 degrees centigrade. They are separate now. I connect them both by the wire here. Now heat goes from this side to this side, and this also become 50, this is also become 50, 50, 50. Both become 50. So this is also spontaneous process. Everybody see that? Yes or no? You got it? Alright, now look here. Spontaneous process. Now X, Y are in contact and the heat flows from this guy to this guy and both become the same temperature. So this is a more dispersed system, more dispersed because that happened itself. You got that? But if I want to collect heat from here and put it here, I need to spend a lot of my energy to do that work. Ever see that? It's just like you can fail yourself, but if you want to pass, we need to put a lot of effort. Yes or no? Yes? So how many hours you study in home? Maybe somebody is studying 5 hours, maybe somebody is 10 hours, maybe somebody is studying 20 hours. So if you want to make an A plus, you really working very hard. Yes, just like that. So if you want to take the heat from this guy and you want to put here toward the hot, you need to work a lot. Yes, but if you want to just get the heat from this to this cold, it happens itself. Just take out a wire and put it there and all it just goes like that. Yes, it's just like the water. Let's say you have a water here in the tank, and then here you have a bucket. You have a bucket here. There is a tap, and open the tap, all water comes down itself. Yes, but if you want to put water from here to here, you need to lift the bucket and go and power in the. Ever see that? Yes, it's just like the water flow or heat flow, energy flow, everything is same. So if higher there is a tank, here is my bottle. I just open this one and put it here. Somebody open there and water come and fill it here, right? Spontaneous, yes? But if I want to put this water to my tank up there, I need to take this end and walk up there and I need to power that. I need to put a lot of effort there. Yes? Ever got that or no? Spontaneous and non-spontaneous. All right. So look here, what it is saying is that, let's say, so this is a more dispersed system. This is a more dispersed. Itself happen and it's a more dispersed. That's a more dispersed. Dispersed. This is a less dispersed. Less dispersed. You see that? Both are less dispersed. When the heat goes this way, then the system becomes whole is a more dispersed. Yes? And then if you look here, maybe this guy has 10 joule energy. Maybe this guy has 5 joule energy. Now total energy is 15 joule. Now here is also total energy is 15 joule. So energy is not changing. You see that? Energy is not changing, but the dispersion is becoming more. Dispersivity is changing. You got that or no? Yes. So this is a more disordered sense change. But overall, there is no change in energy. If this was 10 joule, this was 5 joule, total is 15 joule. Now if you take all energy here and look, that's also 15 joule. Yes? So energy is not changing. So what is changing? Dispersion is changing. Yes? More scattered. People are becoming more scattered. Yes? All right, like that. So the more dispersal is called so more dispersal is called more uniform system. So look here, there is a uniform. Ever see that? More dispersal means more uniformly dispersed. Ever got that or no? Yes? So this class is not uniformly dispersed now. What I could do, this class very stable, so I could put the Rosieri and Rainford, right? Yeah, so two students here, yes? And then I could put Thomas back there. And that's good. Maybe I could put 2 or 3 people from there and I could put there and that could be the more dispersed and stable system. You see that? But we are living being. We are trying to behave according to our will. But if it was we were dead people and we were mobile, we would disperse more uniformly here in this class. Ever see that? So heat doesn't have its brain, so heat disperses. The air doesn't have its brain, so it disperses uniformly. Ever see that? But we cannot be uniformly dispersed. So Boston is too much crowded. Providence is too much crowded. If you go a little bit down toward Kingston, small number of people. Ever see that? So system always try to be in the more dispersed condition. More dispersed means more uniformly distributed. Everybody? Yes or no? So dispersal means they try to be in uniform condition. So uniform means more dispersed. Dispersed, very highly dispersed. Highly dispersed. HIGHLY, highly dispersed. You got that? Highly dispersed condition is more uniform condition. And system always try to be in a highly disordered or highly dispersed condition. People don't want to stay close together. They want to disperse far away, far away. You see that? So if you are an international student, maybe you always wanted to leave your family and wanted to live far away from parents. Yes? It's just like that. You want to disperse more. Good? Good. Now let's go to the next one. In the thermodynamics, a reversible process is one that takes place at such a low rate that is always at equilibrium and its direction can be changed or reversed by infinitesimally small change in some condition. Now let's look what are they doing here. Now let's say this is water. This is water. So cold water. This is a hot water. Hot water. And I have the ice here. That's ice. Ice. You see that? And I am connected ice to water with a thin wire. You see that? So what happened? Heat goes from which side to which side? Hot water to cold water or ice to water or water to ice? Water to ice, right? Hot to. So tiny heat goes from here. Tiny heat goes from here. Maybe 0.0002 joule. Heat goes from here to here. And if I want immediately 0.002 joule, I can just reverse back like that. You see that? So that condition is called reversible. So I need to do very infinitesimally small. Yes? Is that possible? It's not possible. It's just the assumption people thought in the brain. You see that? So we cannot do anything reversibly. Always heat goes from this side to this side and it cannot be flown from ice to water side. But we are thinking that, oh, maybe tiny bit heat I give this way and immediately that amount of heat might be going this way. That condition is called the reversible condition. Everybody see that? So basically, you are just putting heat in a system very tiny. You see that? So that condition is called the reversible condition. You see, everybody see that? So if you go to the market and work in the pizza store, pizza guy, so they are paying you maybe $15 per hour now. Yes? $15 per hour in the pizza store. Now, if they give you $15.05 in the $15.05 In next year, that's a kind of the reversibly. They are giving the money reversibly to you. So they can take it out. Okay, I can make 15 again. So they can easily reverse back, right? Yes or no? And you don't get angry because they just give the 5 cent. So you say, oh, take your my 5 cent, I don't care. Yes? So they can take it back. So they just give you 5 cent more, they can easily take back without making you angry. So that's a reversible condition. You got that? Now let's say they are paying you $15 now, and then they suddenly give you, let's say, $50 from next week per hour. How much they increase? They give a lot of money. Now if they give 50 back to 15, you don't want to go to work. Oh, I don't want to go to work. My $15, you get my $35 out from my pocket. So why I want to work for you? Yes? Everybody see that? So if you give a tiny bit, tiny bit, tiny bit, tiny bit, you can easily reverse that. So that's called the reversible system. But if you give a lot at the same time, it's very, very hard to be back. So that's the irreversible system. Everybody got that? Yes? So I will ask this kind of question in next exam. Yeah? What is reversible? What is not reversible? So you need to say, tiny bit, tiny bit. I go to pizza store and my salary is $15 an hour. Yes? And then my store manager next week increased 5 cent and he started to give me $15 5 cent per hour. Yes? And that is called the reversible process. You see that? If you want, he can take back that 5 cent and he start to give you $15 again. Yes? And you don't get angry. So that condition is called reversible system. But if your salary is $15 an hour, suddenly your from 15 to goes to 50. Do you want to go back from 50 to 15? No way. Yes? So that's a irreversible process. Good? Yes or no? So if you put a tiny, tiny, tiny bit heat or tiny, tiny bit anything in the system, that is called the reversible process, reversible way of doing things. So in Nepal, in our country, so I come from Nepal, in our country, so when I left Nepal, our salary was $10,000 in Nepal. Oh, sorry, not dollar. So this is a rupees 10,000. You see that? Rupees 10,000. And now when I left country, in the next year, they make 35,000 rupees per month. They just give a lot of money suddenly. So they did that irreversibly. You see that? But when I come to United States, the salary was 40,000 for postdoc. 40,000 for postdoc. And then they give the salary in the another year 40,000 $2. That's a reversibly they increase the salary. So the postdoc salary from 2005 to 2023, it is still around 40,000 here. You see that? They tiny bit increase, a tiny bit, tiny bit, tiny bit. So even if they take that my $2, I'm okay to work for them. That's a reversible process. Does that make sense? Yes? All right. Good. So that's irreversible. So they're 10,000 to 35,000. If government say I can't give 35,000, be satisfied with 10,000, all will resign and go home. You see that? That's irreversible. Have you got that? All right. So let's go there. Now this one, what is the entropy? Now we need to define the entropy or the dispersal. Entropy is nothing more than dispersal. If there is a more dispersal, more entropy. Everybody see that? So more dispersed. If something is more dispersed, that's more dispersal. In the morning, I comb my hair so nicely, so I had not a dispersed. So I had a less entropy. So now my hair is all everywhere. So more dispersed. I have more entropy now. Ever got that? Yes or no? Good? Just like that. Good. So now you put a tiny bit it. That Q reversible means, let's say you have water here, and then from you put it in the heater is so cold, very, very cold, a tiny bit warm. Maybe if this is water is 25 degrees centigrade, the heater is maybe 25.5 degrees centigrade. You see that? And then if you put in the heater, a tiny bit heat goes from heater to the water. So that is the Q reversible. Maybe 0.02 joule goes there. So 0.02 joule heat go from here to water, and then that's a 25 degrees centigrade. What is 25? You need to add 273. 25 plus 273 is 298. Now you divide by 298, and that is the change in the entropy. Everybody got that? Yes or no? So what kind of heater I use? Cold heater. So if heater is 20, if water is 25 degrees centigrade, heater is what degree centigrade? 25.5 degrees centigrade, tiny bit warmer than the water. Yes, and tiny bit heat go from heater to water. And how much heat go there? Tiny bit heat means 0.002 joule. And what is the temperature of the water? 298 Kelvin. So the heater give that much heat, and divided by the temperature of the water means the entropy change of the water. Everybody got that? Yes or no? Good. So if you put like this one, so this is, let's say, 25 degrees centigrade, and let's say your heater is like your home heater, like 1000 degrees centigrade. This is I'm not talking like that. I am putting the water in the very cold type of the heater. You see that? It's a too hot. That's a too hot. So it gives a lot of heat here. Ever got that? Yes. So it's like a teacher is also weak, students are a little weaker, and we are learning from each other. So that's a reversible. Yes? If teacher knows too much, students are weak, and if we are trying to do something, that's a reversible. Ever got that? So both are weak kind of thing. Small. So if there is a small difference, tiny bit heat goes from one side to another side. Yes? So if one is a 25 degrees centigrade, another is in 25.5 degrees centigrade, heat goes from 25.5 to 25 degrees centigrade. How much heat goes? Tiny bit. You see that? Tiny bit. And that tiny bit heat divided by the heat of the temperature of that water in Kelvin scale is the change in the entropy. You got it? Yes or no? Good. So, all right. So let's go there. Now, another way, so that's one way of defining entropy. There is another way of defining entropy. That's S, K, L, and W. S is entropy. K is called Boltzmann constant. So that's value is this much. And then Ln is the math function. W is the how many state they are dispersed. So if I am going to calculate entropy of this class, what I do is K, Ln, and then 1 2 3 4 5 6 7 8 9 10 11. So we are dispersing 11 way here. So 11, and then I get the number, and that's called the entropy. So they are defining entropy is two way. You got it? Yes. All right. One is you need to count how many state you are dispersing things, how many ways you are dispersing things. Another is a heat divided by the temperature. Two-way entropy is defined. Everybody got that or no? Yes. So I can calculate the entropy of this class easily. You see that? So S is 1.38 10 to the power minus 23, and that K is, and then Ln is a log function. W is how many way I arrange these people in this room. Yes. Or if I have a I will show you there. So if let's say there are n boxes, n seat, and let's say there are the 11 students in this class, 11 in this class. So n seats. So how many seats here in this class? 30 seats are there. Seat means how many seats here? Like this. How many seats here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27 seats in this class now. Everybody see that? Yes or no? So I just counting the seat. Yes? 27 seats in this class. 27 seats in this class, and I have how many students? 11, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 students. Yes? 13 here. Put this number in calculator. 27, 10, power 13, and then you get a number, and that many way I can arrange the student in this class. You see that? So the Angel is there, I can put him there, or there, or there, or there, there. I can take Thomas there, or there, or there, there. I can arrange one student many ways here. Everybody see that? Yes or no? The way you are sitting in this class is only one way you are sitting. But Angel can come there and sit, or he could sit there, or maybe he could sit there. So if I do calculation, I could put student that many way. 27, 10 to the power 13. Many way. Yes? So now let's go there. That's that W, number of dispersal. Now look here, how many boxes are here? How many seats are here? 2. How many particle are there? 2. 2 student, there are 2 student, 1 student, 2 student. How many seats are there? 1, 2. How many way I can put them there? I can put two student in one seat, and I can leave the seat open. Yes? And then I can put one in one student here or one student here. I can put this guy here, this guy there, or I can put both there. I can put this 2 student in the 2 boxes. I have 2. So how many way? 2 2 student, how many ways? You see that? 1, 2, 3, 4. 4 ways. Everybody see that? 4 ways. Yes or no? So this is one way. So I have 2 seat. I have 2 seat here. I have 2 student here. I can put both student here. Or I can put one here and one there. I can put one there and one here. Or I can put both there. Another. You see that? So 2 student can be arranged in 2 seat by 4 ways. Yes? So that one is a W. So look here. So if I have a 4 student, 2 box, how many way? 2 box, 4 student. So look here. Can you do this one? 2 multiply by 2 multiply by 2 multiply by 2. 16 ways. Ever see that? 2 student, 4 student in 2 seats. I can arrange them in 16 ways. You got that? I could put all 4 in this one seat, or all 4 in another seat, or 3 in one seat and 1 in another seat, and I can just rearranging them, and I can put them by 16 ways. Everybody see that? So this is one way. This is another way. Another way, another way, another way. This is another way. This is another way. This is another way. So I can just keep arranging student, and I can arrange them by 16 ways. Yes? Everybody got that or no? Just like that. So don't worry. So you don't need to do something like this. So you just need to know number of boxes, number of the balls. You see that? How many boxes you have? 2 box. 2 box you have. And how many people you have? 4 people. 1, 2, 3, 4 people. So you could put these 4 people in this 2 room by 16 ways. Ever see that? So they are just counting, and in one they are putting all 4 in one box. They are putting all 4 in another box. In another case, 1 in one box, 3 in another box. In another case, 3 in another box, and 1 in another box by changing color. You see that? Ever see that? That's how we do. Good? So that's called micro state. If you do something like that, that is called micro state of arranging student. So this is the way you are sitting in this class now, is that only one way. Yes? But how many way I can arrange you here? There are 20 seats, and there are how many people? 12 people now, or 13 people here. So there are that many way. 27, 10 to the power 13 is you do that one, it's a big number. That many way I can arrange student here. You got that? The statistics, you don't have to count every time. Now look here. So this is, how many is the entropy change? We use this formula. Delta S is equal to KLN WF by W initial. So what I do is, if I want to change the arrangement of this class, my my entropy change would be like this. K is you go back and look here. K is what is the value of K? K is 1.38 10 to the power minus 23. 1.38 10 to the power minus 23. So that is 1.8 10 to the power minus 23. That's a Boltzmann constant they call Ln. So this is one way of arrangement. You see that? Everybody see that? Now it's a one way. So I put 1 there. And if I could arrange them, how many way? 30 10 to the power 27 seat 10 to the power 13 student, like that. So if you put this number in calculator, you get a number, and that's the entropy change of the class. Have you got that or no? Yes? Now let's go and apply this formula here. Look here. Now look here. How many ways you are distributing things here? Look here. How many ways you are distributing things here? One way. Yes? All 4 box in one box. All 4 guys are. So this is 2 box I have here. At the beginning, I have 4 guys here. 2, 3, 4 guys here. The initial. This is just like this class. Yes? One way. But if you could distribute this 4 guy in 2 box, you should say 2 box to the power 4. That would be how many that is? So this is 16. 4 to. So how they are doing here? Let's calculate the change in entropy of the. Okay, so they are doing this way. So they are not arranging the exactly they want to arrange. You see that? So they are what they are doing is, so they are already. So let me do that one and discard and look here. So how many ways they arrange? So this is one way. So that's one way. So our formula is, so they didn't do many kind of the arrangement. They only did that kind of arrangement. So what is the entropy change? Delta S is equals to KLN W final divided by W initial. W initial. So let's look here. K is 1.38 10 to the power minus 23. Now Ln. So how many way they arrange? 1, 2, 3, 4, 5, 6 way they arrange it. And at the beginning, that is only one way of arrangement. So you put this number in calculator, and that's your entropy change. Everybody see that? So they didn't too many ways of arrangement. They did only that many arrangement. You got it or no? But they could arrange these guys like this way. 2 multi 10 to the power 4. They could arrange them by 16 ways. But they did not. They only arranged them 6 ways. You got that? Everybody see that or no? So at the beginning they have like this. So you go there and look the box. All 4 are in the one. So that's the initial state. Yes? And then you started to, oh, I want to make these arranged by 6 different way. And you did 6 different way. But you could arrange them by 16 different way. You did not. You see that? So that's a final. Final is 6 ways. You got that or no? Yes? What you could do or what you did? You could arrange by 16 ways. But you only arrange them by 6 ways. You see that? Yes? Good. So 6 ways. This is 1 way, 2 way, 3 way, 4 way, 5 way, 6 way. That's a finally you arrange 6 ways. And initially they have put by 1 way. So 1 way, that's a 1 and that's a 6. 6 by 1 or 1 by 6, it gives the same number. Everybody see that? When you do the log of the 1 by 6 or 6 by 1, it gives the same number. But if 6 is up, it gives the positive number. If 1 is up, it gives the negative number. But number comes the same. Everybody got that or no? Log 1 by 2 and log 2 by 1 has same value. But if you do the log 1 by 2, you get minus 0.693. But if you do log 2 by 1, you get plus 0.693. You got that? So there is no difference. Good? All right. So what is the most probable distribution? The largest number of the microstate. So the largest number of the microstate is look here. So I told you, you could arrange this guy by how many way? 2 to the power, by how many way? 2 to the power 4, 16. You could arrange them by 16 different way, and that would be called the microstate. But they did not. So not all microstate are included when they arrange 6 ways. Make sense? So if you have arranged them by 16 ways, that would be called the microstates. Everybody got that? So whatever this number gives by this number, that is called the microstate. That's the maximum way we could arrange things. The most probable distribution has the largest number of the microstate. So 2 to the power 4. You see that? That's the maximum number of the number of the arrangement, and that would call the most probable. So most probable would be 2 to the power 4. That is 16 there. 16 microstate is the most probable. Yes? So if you did the most probable, we call the greatest entropy. So this class now is a very, very small entropy. Yes? So if I want to increase the entropy of this class, I just stand up that guy and put it here, stand up her and put it here, stand up there and put it here, and I could just keep doing crazy thing here, and I could increase entropy a lot. Everybody see that? So the craziness is the entropy. But if somebody is meditating and very silent, no entropy. Is that? I want to be something like a very low entropy person. You got it? So when you have a lot of money in future, you want to retire, you want to go to the village side, get a small house and just sit there and repeat the God's name. Yeah. So that's a low entropy state. Yeah. Now we are in the crazy state of the entropy because we are trying to make money, trying to pass, trying to get a good grade, trying to make money, go to work. You see? So this is a highly disordered condition we are now in. Everyone there? Just like good. All right. So high entropy, always system try to be in the crazy busy state because that's the most likely thing what happened in nature. Everybody see that? So people are crazily working, crazily behaving. Yes. So always system tries to be in the highly probable state. That's a highly disordered state. Yeah. Most crazy. So from today, when you go home and you see some bad people, you don't want to tell something bad. Oh, that's how the system works. Everybody want to be crazy. Yes. All right, like this. Now look here. So if the initial, put that formula. So S is equal to K ln W initial, like that. So you get the entropy of this class. Now, yes? Everybody see that? Yes or no? And then you could also do S, when you do S is equal to K ln W final, which would be, that WF would be, I have 20 seat, 7 seat, 13 student. When you do that one, you get the final entropy. Yes? And then put that final here, and this is a 1. This is only one way we are sitting here. Yes? So this is 1. And then you put that number, S final and S initial, you can get the change in entropy. Or you don't have to do this. You already can do this like that. The delta S is equal to K ln W final by W initial. We already did that. Either way is fine. Either you do that way, or delta S is equal to S2 minus S1. So both are same. You got that? Have you got that or no? So saying this one and saying this one is same. You got that? Yes? All right. So entropy depends in what factors? The phase of the substance. So if you have a solid, they are tightly, clearly, nearly arranged like that. Less entropy. Less entropy. But if it is a gas, they are crazily moving. High entropy. Everybody see that? Yes or no? If the solid, the particular nicely, tightly packed, nice arrangement, so less entropy. Good? But if the gas crazily moving, high entropy. Everybody see that? All right. Now, temperature of the substance. Let's say if this is in the 25 degrees centigrade, the molecule are slowly moving like that. Slowly moving. But if it is in 100, they are crazily moving very, 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 very fast. So the high entropy. Yes? Everybody see that or no? If the temperature is high, they are crazily moving. Crazy fast moving is called high entropy. Yes? You got it? Yes or no? Fast means high entropy. All right. Higher temperature, particle move more fast and everywhere. More freedom means everywhere. You see that? You got it or no? Just like that. So if the temperature is higher, entropy is higher because particles are moving faster everywhere. Yes? And then if the temperature is lower, the molecule are not moving fast and entropy is lower. Temperature is important here. Yes? And if it is a solid, particles are arranged one way, only one way, low entropy. But if it is a liquid or gas, crazily moving many ways. So that's a more entropy. You got that? Good. All right. So now look here. This is a crystalline, less entropy. So maybe entropy of this guy is 2. This is liquid. Maybe they are moving faster. Maybe entropy of this guy is 5. This is more crazily moving. Maybe entropy of this guy is 10. Everybody see that? Yes or no? Good, like that. So if you look here, 5 minus 2 is 3. So going from here to here, entropy change by 3. Going from here to here, entropy change by 10 minus 5 is 5. You see that? Entropy change. What is entropy change here? Look here, the entropy of this guy is, I said 2. The entropy of this guy is 3. Entropy of this guy is 4. So which has the highest entropy? Gas has highest entropy. What is the change in entropy from liquid to gas? 4 minus 3, 1. Yes or no? You got that? Is it greater than 0 or less than 0? 4 minus 3. Greater than 0. Look here. Going from liquid to gas, entropy become 1 more. So it's a greater than 0. Yes? Now look here. The entropy here is 2. Entropy here is 3. 3 minus 2 is a 1. Greater than 0 or less than 0? Greater than 0, right? 3 minus 2. 3 minus 2 is a 1, right? So going from a solid to liquid, entropy is more than 0. Going from liquid to gas, entropy is more than 0. Yes? Now let's go another way. 2, 3, 4. Let's go another way. So this is 4, this is 3. So 3 minus 4. Going from here to here is 3 minus 4 is how much? Minus 1? Yes or no? 3 minus 4. Yes? 3 minus 4 is minus 1. Less than 0. You see that? Going from gas to liquid is minus 1, which is less than 0. Yes? Now go from liquid to solid. In the liquid you have 3. And this is 2. 2 minus 3 which would be minus 1, less than 0. You got that? So if you go from solid to liquid, entropy is plus change. And then if you go from liquid to gas, entropy change is plus. But if you go from gas to liquid, entropy is minus. Minus change in entropy. Entropy decreases. And if you go from liquid to solid, entropy is minus 1. Entropy decreases. Minus 1 means decrease. Ever got that or no? Simple, yes? Ever see that? Yes? So just subtract it from initial to another. If it comes to be minus number, smaller than 0. Entropy change is smaller than 0. Yes? Good? So it could be a one potential exam question. So let's put here. So I have a so let's look here. So this is like this. So here is ice. Ice. This is water. Which has more entropy, ice or water? Solid or liquid? Water, right? So maybe water is 10, entropy is 10. Ice entropy is 2. So if you go to ice to water, 10 minus 2 is 8, plus 8. You see that? So this guy has 8 more entropy than ice. Yes? Have you got that? Very simple, right? Now, if you have the water, so let's say this is water. Water, you have the entropy here is 10. Now you want to put in freeze, and in the freeze it becomes solid, and ice, this is ice. Now you need to subtract from 5 to 10. 5 minus 10 is minus 5. So the entropy decrease from going water to solid, ice. Ever got that? So always you need to, from the product side to the reactant side, or the final side to the initial side, you need to subtract. Yes? And whatever is the entropy, you should give the plus or minus sign. Yes? And if the plus sign comes, entropy increases. If minus sign comes, entropy decreases. Got that? All right. So let's go here. Now system is surrounding. Now let's look this class. So this is a class. This is a class. And in this class, Thomas is here. So see is Thomas here. I am making Thomas here. You see that? I want to study about the Thomas, not other people. Ever see that? So Thomas is a system. Thomas is a system. System. Because I want to study about Thomas. You see that? What I want to study is called the system. And everything in this class, including everything, me, benches, light, and every other thing here, that's called the surrounding. Surrounding. You got that? and the surrounding plus system, everything, this class is called the universe. Yes or no? You got it or not? Yes. For example, I want to study anybody. So I want to take Gabriel and he is my system. And everything other is a surrounding. And if I want to talk surrounding and system together, I give this class name as a universe. You got that? Alright, so let's go there. So there are two things. You see that I am talking about Thomasy here, C system, and I am talking except Thomasy here, that's all surrounding. And what is happening to this whole class? That's a universe. Everybody see that? So the change in the uh, entropy of this universe is equal to change in the entropy of the system. What is Thomasy doing and what other people are doing? So that's how I need to calculate that. Everybody see that? So change in the entropy of this class is the sum of the change in entropy of her plus the change of entropy of every other thing here. You got that or no? Yes? So very important. Now let's go there. This is, and if I do that, so I do this everything, and then when I calculate the value of delta S universe, always I get a positive number, maybe +1, maybe +2, maybe +3, maybe +50. You see that? When I do this calculation, I always get a plus number, and that's called the second law of thermodynamics. So if you are looking for the entropy change of the Thomasy and the entropy change of the class, and you are adding or subtracting this two number by somehow, and if you get a plus number, that's the entropy of the universe is increasing. That's called the second law of thermodynamics. Everybody got that? So that's a, if this the whole class, I'm not saying her, I'm not saying the class, I'm saying her plus the class. So if entropy is I did all consideration, entropy of this class is always increasing. You see that? So entropy of the universe is increasing, always plus. We are trying to be more disordered. So that is called the second law of thermodynamics. Who didn't get this idea? You got it? So I will show you here. Now let's look here. I just want to do this one. Look here. Delta universe, it is becoming more. So when I calculated, I put number 3 here, I put 2 here. So maybe that 2 is a -2. 3 minus 2 is what? +1? Yes or no? 3 minus 2 is +1, right? That's a plus number. So delta universe is more. So that if this is the case, the process is spontaneous. It's happening itself. You got that? Now if you see something like this, so let's say something like this. So this is um, uh, 2, this is -5. This is coming a what? 2 minus 5 is -3. You see that? The delta universe is coming to be -3, less than 0. This process is not happening. Got it or no? Yes? You got that? Good. Not happening. Now let's look here. So this is 3. This is also 3. 3 minus 3 is what? 0. Yes? So if that is the case, the process is in equilibrium. Nothing is happening. Who didn't get that? So find the change in entropy of Thomasy and find the change of entropy of everything and subtract from Thomasy's one number to another number, and if you are getting the plus, you are that's a spontaneous process. If it's a minus number, it's a non-spontaneous process, and if you get 0, that's an equilibrium process. Nothing is happening. Does that make sense? So who is a minus number? Who is a minus number? I am talking about Thomasy here, right? So C is losing her entropy. So C is a minus number. And class is getting the plus entropy. So she doesn't want to stand up, but she wants to agitate the class. So her entropy is low. Now she is now moving, right? So she is in the 0 state. And then now she wants to do something like this. So her entropy increase. So your entropy should decrease. If her entropy increase, all other entropy decrease. So one is always increasing, another is always decreasing. Ever see that? So if one entropy is increasing, another. So if this guy, if system entropy is increasing, surrounding must be decreasing. If surrounding is decreasing, this must be increasing. You see that? Therefore, decreasing to the decreasing entropy, I give the minus number. Increasing entropy, I give the plus number. And one is plus, another is minus, and I get two number. And if I get the minus, that's a entropy. That's a non-spontaneous. If I get the plus number, spontaneous. If I get the zero, that's a equilibrium condition. Nothing is happening. Make sense? Both number cannot be plus. You see that? If my entropy is decreasing, yours must be increasing. So I am minus 5, you are plus 5. Or maybe plus 7. I don't know. You see that? My entropy, since I am talking, my entropy might be increasing. I don't know. So let's look here. So if I am a system here, I am going to look here. So look here. So we are, so I am the system here. I am the system here. So my entropy, I'm just talking a lot. So my entropy might be increasing by 10. You see that? I'm more in the disordered state now. Everybody see that? But you are just tightly sitting and your entropy might be decreasing. You see that? So my entropy is increasing actually. I'm more crazy now. You see that? I'm just talking too fast and I'm just walking around. Yes? So my entropy is increasing. So if my entropy is increasing, your because it's because of you. You are making me to increase my entropy. You see that? So your entropy might be decreasing by 2, like that. Decrease is minus 2. Everybody got that? Plus 10 minus 2 gives me plus 8. So this system is spontaneous. So everything what happening in this class is spontaneous itself. You got that or no? Yes? Yeah. Now if I do another way, so let's this one. So you guys, your entropy is decreasing, let's say by 10. My entropy is increasing by 10. My entropy is decreasing by 2. So you see that 2 minus 2 plus 10 would be plus 8. That would be, so this is my, I'm system, you are student, you are surrounding. So minus 2 plus 10 gives 8, and that's this system is the spontaneous. Now if I am 20, you are 10, minus 20 and plus 10 would be minus 10, and that would be non-spontaneous. Everybody see that? Yes or no? Now, if I am decreasing by 20 and you are increasing by 20, and 20 and 20 gives you 0, and that means that's equilibrium. So how much I am losing, that much you are gaining. Entropy is same thing. Everybody got that or no? Yes? So one is losing entropy, another is gaining entropy in the system, in the universe. Universe is system and surrounding. So if I am a system, you are a surrounding, like that. Yes? And you and me make this universe. Everybody got that? All right, good. Now, third law of thermodynamics. Now, if you take the crystal like this, so let's say this is a crystal of solid. So this is solid. Cool this guy to minus 273 degrees centigrade, which is a 0 Kelvin. 0 Kelvin, and it has a zero entropy. Zero entropy. This is called third law of thermodynamics. Everybody got that? You have a solid and you need to cool at what temperature? Minus 273 degrees centigrade. And how much entropy is that solid has? 0. So everything is frozen. Nobody is moving. So that's called the third law of thermodynamics. Everybody got that? Yes? Take a solid, put in very, very cold place. And what should be the temperature of that system? That cold place? Minus 273 degrees centigrade or 0 Kelvin. So in that condition, what is the entropy of that solid? 0. So that is called the third law of thermodynamics. Entropy of everything at minus 273 is 0. Yes, entropy is 0. Look here. What they are saying? Third law, the entropy of a pure perfect crystalline substance at 0 Kelvin is 0. At 0 Kelvin, entropy is 0. Entropy is 0. Entropy 0. A crystal, you take a crystal of the sodium chloride, put in the very cold environment, minus 273, yes? And that condition, the entropy of that crystal is 0. 0 entropy, we call that, yes? So all the particles of that crystal are frozen. They are not moving. Now standard entropy. What is standard entropy? All right, so maybe we cannot finish it today. We will finish in next class. Let us talk about the standard entropy. So look here, standard entropy is you take 1 mole of substance. So 1 mole of substance, you need to put you need to put 1 mole of substance. This is a beaker. In this beaker, put 1 mole of substance. 1 mole of substance. So if it is a carbon dioxide gas, put 44 gram. 44 gram of carbon dioxide is 1 mole. 1 mole. If it is a carbon dioxide, 44 gram. Take a beaker, put 1 mole of substance in 1 mole of substance in that beaker at 1 bar pressure. So if you put the pressure gauge here, it shows a 1 bar. 1 bar, and if you put a thermometer here, the thermometer shows 298 Kelvin. So that is called, how much entropy is there? That entropy is called standard entropy. Ever got that? So take a beaker, put 44 gram carbon dioxide, because 44 gram is the 1 mole of carbon dioxide. Put a pressure gauge there, that guy should show 1 bar pressure. Yes? And put thermometer there, that thermometer should show 298 Kelvin. Yes? 298 Kelvin or yes, 298 Kelvin. So in that case, we call that entropy is a standard entropy. You got that? Standard entropy of carbon dioxide. Now let's look here. If you are taking the salt solution, let's say this is a water and you are putting the salt, NaCl. So molar mass of the sodium chloride is 58. So basically it's a water and you are putting the 58 gram of sodium chloride in 1 liter water. So that's a 1 molar solution. And if you are defining the entropy of that there, that is called the standard entropy. Everybody got that? 1 mole. Take 1 mole of anything in water solution, 1 molar solution, and that entropy at 298 is called the standard entropy. Got that? Definition, yeah? So they define the standard entropy that way. Everybody got that or no? You need to either take the 1 mole of gas, or you need to take the 1 molar solution. And if you are looking the standard entropy change, we just final entropy minus the initial entropy. Same thing. Look here. Now let's look here. I am going to write here a reaction here, H2 plus O2. So I am going to do this one, yeah. H2 and O2 gives H2O. H2O here in standard condition. Let's say entropy of this guy is 50. Let's say 2. Let's say entropy of this guy, standard entropy of this guy is 30. Let's say standard entropy of this guy is 10. So what would be the entropy of this whole guy? 2 multiplied by 10 would be 20. Look here, 20 and 30 is 50 and 50. So product minus the reactance. So 50 minus 50 would be 0. That's called the standard entropy change. You got that? Yes or no? So let's look again. Standard entropy change. So I need to multiply with that coefficient to that number also. Yes? So I will put some problem in the later I have, so you will see there. So I am going to write it again. Maybe I can just make a little bit H2 and O2, H2O. So this is my reactant. So if I balance this, there is 2, there is 2. Now it's a balance. Now let's say standard entropy of this guy is 10. Water is 10. So how many are there? 2. So I need to do that. 20. Standard entropy of water is 20. If there is a 1, standard entropy of this guy is, let's say, 50. And then how many is, there is a 1. You see that? And let's say standard entropy of hydrogen is 80. How many are hydrogen there? 2. So like that. You need to do like this. You see that? And then from this, 2 multiplied by 10 is 20 minus 2 multiplied by 80 my plus 1 multiplied by 50. Whatever you get this number, that's called the entropy change for this reaction. You got that? Yes or no? The exam question, yeah? So make a note. So you need to do the balance. I mean, I give the balance and you need to just add all number from the product side multiplying with that number as well. And you need to add all from the reactant side and then you need to get subtracted. Everybody got that or no? Yes? Good. Always from product side, this side to that side. You got it? All right. So like that. So the book make things unnecessarily complicated. I already told you. You don't have to do this one. If that entropy change is more than zero, that's the uh, second law of thermodynamics. If you calculate if the delta S universe is always greater than zero, that's a spontaneous process. So entropy of the universe is always becoming positive. So we are becoming more chaos and more chaos and more chaos. You see that? If in Providence there are no policemen, what would we do? We would drive crazily everywhere, kill each other everywhere. Yes. So the policeman is trying to make system in order by decreasing the entropy. Yes. But if we don't have the law enforcement, there would be chaos everywhere. So the universe is in the chaos condition. So it's the universe entropy is always increasing and increasing itself. Ever see that? Universe means star, sun, moon, earth, everything. I'm talking about everything of the universe. They are just moving farther and becoming more chaos and chaos. You got that? So that's the second law of thermodynamics. The entropy of the universe is increasing more and more. It's always more than zero. Got it or no? So it's just like a universe. If my head is the universe, this morning my head was nice, but now it's already like that. Now I have a class is 3:30 and I finish in 6 o'clock. My hair is all bad and I'm just flat. So you see that entropy of the universe is increasing. Everybody got that? So if I have something here, let's see how much time I have. Maybe 5 more minutes. So in the next class, I will talk about the Gibbs free energy and finish this chapter, and probably I will finish the chapter 17 also. That's a very tiny battery chapter. Yeah. So I'm a battery champion. So I did a lot of battery research. So I know everything about batteries. Yeah. So I will teach that, and I will do some math, and we will finish the class probably in the next Tuesday. And then next week, when we come after the Thanksgiving, we do a little bit review about exam and whatever, yeah. And then we take the quiz in the next week of the Thanksgiving, and then after the next week Wednesday, we will take the exam 3, and then next week we meet one day, and we don't have to see each other. We will be done, right? All right, everyone. So, ever see that? Any question? So what I'm saying is this one. So the Thanksgiving. So Thanksgiving next week. Next week, uh, Thursday quiz. I will put announcement. You see that? It'll be online. No, we'll come here after Thanksgiving. Yes, after Thanksgiving next week. You see that? And then are we meeting on Tuesday? I think we are meeting. Yeah, we have class. Yeah. We are meeting every day, yeah? So we review and whatever is not covered. Like next week, but the week after. The exam. Okay. Yeah, but we are meeting every class day until the second week of the December, according to the syllabus. Yeah, but we meet on Tuesday, but not Thursday. Not Thursday, because that's next. Yeah. The next week of that. Yeah. Tuesday and Thursday. Yeah. And then we have the third exam. Third exam in December 1st. December 1st week. So the third exam is our final exam. No, the final and the final week. We have a cumulative exam of all three. Yes, yes. All right. Does that make sense? All right.